Okay, in previous lecture, we have discussed some certain numericals uh, for stepper motor or from stepper motor. In that numerical, we have discussed how to calculate the different parameters of stepper motor like a step angle, resolution, revolutions per minutes, revolutions per second, then the stepping frequency, stepping rate. So the numericals may be asked for 5 marks in question number one, that is in compulsory question, or maybe a 10-mark numerical in remaining questions. Okay. Now that completes the characteristics and parameters part of the stepper motor. Now let's move towards the last bit of stepper motor chapter, that is the control strategies of stepper motor. Okay. So in this particular control strategies, we are going to discuss total three control strategies of stepper motor. That first one is the open loop control of stepper motor. Second one is the closed loop control of second motor, and third strategy is microprocessor based control of stepper motor. Okay. So question might be asked for 5 marks on each control strategy. Write a short note on any one of the control strategy out of these three, or maybe 10-mark question in which you have to explain any two control strategies. Okay. So there is a simple block diagram for each control strategy, and from that particular control strategy, you have to explain the actual working. From that block diagram, you have to explain actual working. Now, what is meaning of control? As we know that in stepper motor, we have to provide excitation to the stator phases according to the mode of excitation. So this particular excitation which is provided to stator phases, that excitation depends upon uh, the required step angle, how much step angle we required for the particular stepper motor, and what will be the stepping frequency. That means how much steps should be completed by the stepper motor for a particular time period. So that is actually stepping frequency, or we also term that term as a revolutions. Sorry, resolutions. Okay. So depending upon these resolutions, stepping frequency, stepping rate, and required step angle, we have to provide the appropriate pulses to the phase stator phases of a stepper motor. Now, these stator phases are generally excited with certain power semiconductor devices, which are generally termed as a switching devices. So, these switching devices might be SCRs, IGBTs, or that may be power MOSFETs. And for the particular power MOSFETs to be switched on, that means to excite a particular phase, we have to simply switch on the power MOSFET or power switching device which is connected in that particular phase. So these power switching devices generally works on the gate pulses. So whenever we provide the gate pulse to that particular power switches, then and then only that power switches will work and that power switch operates. So to provide that particular gate pulse, we have to simply drive the gate driver circuit, and how to drive that gate driver circuit, that is actual the control strategy. That means according to the mode of operation required, or according to mode of excitation required, according to the step angle required, we have to simply excite these gate driver circuits. That gate driver circuits will give the appropriate gate pulses to the appropriate power switching devices, and that will simply switch on the particular stator phase, and accordingly we achieve the required mode of operation from the stepper motor. So that entire thing is generally termed as a control strategy for a stepper motor. Now there may be the open loop control or closed loop control. So I think you are familiar with this open loop system and closed loop system because you have already studied that particular part in control system. So basically in open loop control, there is no any control on output which is provided from the system. That means whatever step angle by which that stepper motor will rotate, so that step angle rotation is not taken as a feedback to the actual actuator circuits. Okay, so that is the open loop control. So the excitation control of a stator phases does not depends upon the actual step angle by which that stepper motor will rotate. So there is no any closed loop feedback loop in open loop control of stepper motor. So simply depending upon the excitation which is provided to the particular stator phases, the motor will operates or the motor will rotates with a desired step angle. So this step angle is not taken as a feedback, and that step angle where rotation is not provided as one again input to the excitation control system in open loop control systems or in open loop control of stepper motor. Whereas in case of closed loop control, the position of the particular rotor is generally sensed by the position sensing devices or position sensing elements, and this particular position is again feedback to the input commands, or that will given as a feedback to the input system. Actually, that input system is the digital comparator and translator circuitry. So this actual position of rotor is sensed by position sensor, and the appropriate command is given to input side translator and digital comparator. Actually, that position sensing is called as the discriminators. So this discriminator generally gives the input command or the feedback signal to this input translator and digital comparator, and accordingly the uh, position of that particular rotor will you can say that finalize for the second steps. So after first step only, after completion of first step, the second step is initialized in the closed loop control of a stepper motor, because for second step initialization we required the actual rotor position after the first stage or first step of excitation. So once we excite the motor with a first step, when the motor rotates with a first step angle, after that this particular position of rotor is sensed by the discriminator circuitries, and this particular position is given as a feedback to the input excitation circuitry so that it will provide the second step. So generally in case of closed loop control of a step, the new stepping command is excited, or the new command for the excitation of phase is given only after the previous command is fulfilled. So once the previous command is fulfilled, then and then only we generally provide the new excitation command to the stator winding. Okay. So the first step takes certain more time due to the inertia of this load and motor, and after this particular completion of first step only, we generally provide the second command to the second command of excitation to stator winding. Okay. So yes, I have not shared anything on screen. So only the Google Meet window is there. Okay, till I have not shared any PPT or any PDF. Okay. Yeah. So now screen is visible.
Yes, sir.
Okay. So let's start with the first control strategy for stepper motor, which is the open loop control scheme for the stepper motor. So the block diagram for open loop control scheme of a stepper motor is as shown in figure. So if you look this particular block diagram, there is no any feedback loop provided. That means whatever stepper motor position, rotor position is there, that rotor position is not sensed at the output side, and that sense feedback is not provided to the input logic controllers in case of open loop control of stepper motor. Now, if you look this block diagram, then the three simple elements or three important elements are present in this open loop control scheme of stepper motor. The first important element is a logic controller, and this logic controller is the combination of a different JK flip-flops. I think all of you are familiar with the JK flip-flop. You have studied that JK flip-flop in digital electronics. So JK flip-flop generally has two inputs and two outputs. Okay, and there is a one clock signal. Okay. Now, if you recall truth table for that JK flip-flop, then can anyone tell me what is truth table of JK flip-flop? So what are the inputs? Input provided for the JK flip-flops are J, K, and there is a output only, that is output is Q. So what is the truth table? Truth table for JK flip-flop, when both inputs are low, at that time the output is actually Qn. When any one of the input is high, that is when j is equal to 1 and k is equal to 0, or when j is equal to 0, k is equal to 1, under that case the output of that jk flip flop is equal to 1, that is jk flip flop output is high. So q bit goes high. Whenever both inputs are high, that is whenever both input j and k, both inputs are high, then actual output is qn bar. Okay, so this is the truth table for the jk flip flop. So this logic controller is generally combination of this jk flip flop and gates and or gate. Okay, so depending upon these inputs which are provided to this jk flip flop and input which is provided to this AND gate and OR gate, the excitation pulse is initiated for the particular phase. And to provide this excitation pulse for the particular phase, we required two inputs for the logic controller circuitry. So that two inputs are, one input is the step input. That step input is nothing but the required step angle for the stepper motor. So whatever required step angle is there, accordingly we provide this step input to the logic controller. And second input is the direction input. That direction input is nothing but in what particular direction we have to run that motor. So this step input and direction inputs are provided to the logic controller. According to the logic controller, inputs which are provided to this logic controller, the JK flip-flop will initiate the required pulses. So if we consider, suppose we consider a three-phase motor, three-phase stepper motor, that means that three-phase motor consists three phases on stator, and three phases means, I think now you are familiar with this stator construction. There are total 6 poles and 3 sets of 6 concentric windings placed on that 6 poles, and diametrically opposite coils are connected in series so that there is a formation of 3 phases. So we consider this 3-phase stepper motor. So the controller requires the 3-phase or controller, generally this controller generates the 3 excitation pulses which are required for 3 phases. Say we consider that excitation pulses for say R phase, Y phase and B phase. For simplicity we rename that 3 phases as R phase, Y phase and B phase. So there is a separate control logic for R phase, Y phase and B phase. So these particular control signals which are initiated by logic controller, that control signals are given to amplifier. So second one is the amplifier. So second important block is amplifier. That function of this amplifier to amplifies the control excitation signal which is generated by this logic controller. This amplifier simply rates the level of this signal, okay, and then this amplified signal is given to power controller. Now what is this power controller? Power controllers is generally combination of a different power semiconductor switching devices, that may be of MOSFETs, that may be SCRs, or that may be IGBT. So each of the excitation pulse which is generated by this logic controller, say for R phase we generate excitation pulse for this R phase. This R phase pulse is given to the gate driver circuit of the switch, power switch which is there in R phase of stepper motor stator winding. So whatever stepper motor stator winding R phase is there, so that R phase is excited with the gate pulse which is initiated by this logic control. That means if we simply draw this particular diagram, general schematic diagram for this motor, then this is the R phase, say, then this is the Y phase, and say this is B phase. Third phase is B phase. Okay. So I think you are familiar with this switching circuit. We have discussed this switching circuit in variable reluctance stepper motor. Yeah. So whatever control signal circuitry or control scheme which we are talking about, that control scheme is nothing but simple. The control which is provided to the gate circuit of this power controller switches. Okay. So this particular gate signal is actually provided through this logic controller and amplifier circuitry. So this, whatever, suppose we have to excite say R phase, under this particular case the R phase gate pulse is initiated, that means amplifier excitation pulse is initiated, amplifier amplifies that excitation pulse which is initiated by this logic controller, and this particular excitation pulse is given to the gate driver circuit of the switching device which is connected in R phase. Okay, accordingly that gate driver circuit gives the gate closing pulse, and then R phase get excited. In that similar way we excite Y phase and B phase. So this is the general block diagram for open loop control scheme of a stepper motor. Okay, so whatever thing which I have explained now, that things we can summarize. Say whatever logic controller is there, that logic controller generates the program logic sequence which is required for operation of stepper motor. Now this power controller is consist of the switching devices, and that switching devices are turned on at the particular step in the logic sequence. That logic sequence is generated by this logic controller. Okay, now whatever the logic sequence which is generated, that logic sequence signal get amplified by using this amplifier. The signal from logic controllers are fed to the base gate drive circuits. Actually that is the gate driver circuit of semiconductor switches. I think you are familiar with this gate driver circuits for semiconductor switches. You have studied that semiconductor switches, the construction, working, then different gate driver circuits in semester 4 subject, that is power electronics device and circuit subject. Okay, so there are different gate driver circuits. That gate driver circuits are now available in different gate driver ICs. So we can directly provide the input pulse which is generated by this logic sequence or logic controller to that gate driver IC. According to that input pulse, the gate driver IC will close the particular switch which is connected in particular phase, and accordingly the stator phase of that particular phase get excited, and the motor will run or motor will rotate with a desired step angle. So that desired step angle is provided as an input to this logic controller. Now when we consider say single phase on mode, let us consider we suppose consider the variable reluctance stepper motor. So 3-phase variable reluctance stepper motor with a single phase on mode. Now what is meaning of this single phase on mode? Single phase on mode means one phase is excited at a one particular time. If we have to rotate or if we have to excite another particular phase, then at that time we generally de-energize the initial phase and we excite another phase. That means say in this particular case, suppose RYB 3 phases are there, then initially suppose we excite R phase keeping Y phase and B phase under de-energized condition. Now in next particular sequence we excite Y phase by simply de-energizing R phase. For that purpose simply we have to open the switch which is connected in series with R phase. Okay, so we consider the single phase mode of operation, and let's say we realize this particular sequence for clockwise direction. So for first step R phase is under on condition, remaining two phases are under off condition. For second step, say that means say step is what? It is the desired step angle. Say for this motor, step angle is suppose 30 degree. Okay, step angle is suppose 30 degree. Now for first step, motor will rotates by 30 degree in say clockwise direction. When R phase is excited, remaining two phases are under de-energized condition. For second step, we simply de-energize R phase winding and we energize Y phase winding, so that motor will runs with next 30 degree in clockwise direction and so on. So for third step, we energize B phase, so that motor will rotates by 90 degree. Now if we have to reverse this particular direction, simply we have to reverse the sequence of excitation which is provided for the phases. So initially if we excite R phase, then we have to excite B phase and then we have to excite Y phase. Okay, so if we reverse this particular phase sequence, the direction of rotation for motor get reversed. Now this is the logic controller for the particular circuitry. We are not going to discuss this logic controller in detail. So as I have already explained, the logic controller is made up of the flip-flops. So one flip-flop set is there for each phase. Now the output of this first flip-flop is given to input to the second flip-flop through the AND gate and OR gate connections, and according to these particular sequences, the input will generated for this different phases, that is Y phase, B phase and R phase. Okay, so this is general logic controller which is provided for the stepper motor. Now this part is not in detail for your syllabus. Still I will provide the material for this logic controller circuit. You can go through that material for better understanding. Okay, I'm not going to explain this particular part in detail because that is not mentioned in your syllabus. Now we are going to discuss about the power controller circuitry. So third one is the power controller block. What is this power controller? Power controller block generally consists the semiconductor switches for each phase. So here we generally use a MOSFET as a semiconductor device. Okay, in some cases IGBTs are also used as a switching devices for the particular phases. So say this is R phase, Y phase, B phase. So for all three phases, we generally provide the semiconductor device for each phase and this particular R phase. Now, if you look this logic controller, then after first flip-flop, there is a excitation pulse provided to this R phase. So this R phase excitation pulse is generally given to the gate of power switch through gate driver circuit. Okay, through gate driver circuit, this particular R phase excitation pulse is given to the power gate driver circuit of MOSFET which is connected in R phase. Y phase excitation pulse is given to gate driver circuit of MOSFET which is connected in Y phase. B phase excitation pulse is given to gate driver circuit of MOSFET which is connected to B phase. Okay. Now, according to the logic sequence which is received from this logic controller, the particular MOSFET will turn on and that will energize the particular phase winding, and according to the step angle and according to the direction input which is provided to this JK flip-flops, the motor will runs with the desired step angle. Now this is open loop control scheme. Why we know, or why we term this particular scheme as an open loop control? Because we are not going to sense the position of rotor and the particular displacement of that rotor from initial position using some discriminator circuitry. So whatever sequence logic which is developed by this logic controller, that sequence logic does not depends upon the actual position of rotor. Okay, so as the sequence logic is not depends upon the actual rotor position, therefore this particular scheme is generally termed as a open loop control. So whenever we are going to closed loop control, then in closed loop control, the logic sequence which is generated by the logic controller is generally depends upon the inputs which is provided to this logic controller as well as the actual position of a rotor after a first step. That means when we apply first step to that rotor, then in that first step, what will be the actual position of rotor? So on that particular actual position, this position of a rotor is depends. Okay, or excitation pulse which is, that means the logic sequence which is generated by this logic controller is depends. Okay, so that depends upon the input which is provided to the logic controller circuitry as well as the actual position of rotor after giving excitation pulse to that rotor. Therefore that scheme is actually closed loop scheme. But here the logic sequence which is generated by this logic controller, that only depends upon the inputs which are provided to this logic controller. That does not depends upon the actual rotor position after provision of first excitation pulse to the rotor stator winding. Motor stator winding. So as the logic sequence does not depends upon actual rotor position, this particular scheme is known as open loop control scheme of stepper motor. So if question asks for 5 marks, explain open loop control of stepper motor, then simply you have to draw this particular block diagram. This block diagram is only enough for open loop control, and then write down this truth table or logic sequence table for clockwise direction and anti-clockwise direction. There is no necessity of drawing logic controller and power controller circuitry if question is there for 5 mark or 10 marks. So only block diagram, its explanation along with the logic sequence table for clockwise and anti-clockwise direction is enough. For addition to this, you can draw this particular switching circuit diagram in addition to this block diagram. Okay, so that is again not compulsory. If those who are interested to draw this particular switching diagram, they can draw this switching diagram along with block diagram of open loop control scheme. Okay, so that is about the open loop control scheme. Now let's move towards the closed loop control scheme of a stepper motor. So as I have already explained, in closed loop control strategy, the logic sequence which is generated by the logic controller, actually that logic controller is known as translator here. So whatever logic sequence which is initiated by logic controller depends upon the input which is provided to this translator circuitry. That inputs are generally the desired direction and the required step angle or the required number of steps. So this output of this logic controller depends upon input which is provided to this logic controller as well as the actual position of rotor after first step. So here in closed loop control scheme of stepper motor, whatever new command which is provided for the excitation of a particular phase is given only after the previous command is fulfilled. That means initially we provide a first command. After that first command, rotor will rotate with a desired step angle which is provided in that particular command. After completion of this particular first command, now the position of this particular rotor is sensed and this position signal is given to the translator circuit so that it will initiate the second command. So along with the inputs which is provided to the logic controller circuitry, there is one more input required. That input is the actual position of a rotor after receiving first command to any one phase. So in closed loop control scheme, the new command of exciting a phase is given only after the first command or previous command is fulfilled. So the first step takes the more time due to the inertia of load and motor. So the command for second step is given only after the completion of a first command. That means after first command, the rotor will rotate with the desired step angle, and then this particular rotor position is sensed by the position sensor, which is actually known as the discriminator circuitry, and then only the second command will initiate it. Okay, the second step takes a lesser time than that of the first command. Again, after second command, we initiate the third command. So this third step again requires a still less time than that of the second command, and so on. Thus, the step duration varies as the step advance. So there is a variation in the step durations whenever we provide the advance commands to the stepper motor phases. Okay, because advance command is only provided after completion of a first command. Okay, now to decide this exact time of inputting the commands for the successive steps, we have to sense the rotor position. Okay, and that rotor position should be known, and this rotor position is generally sensed by the position sensors. Okay, so the circuit which enables the position sensing is generally known as a discriminator circuit. So this discriminator circuit is generally consists a position sensor. Now I think you are familiar with the position sensors. So this discriminator circuit generally consists a thin opaque disc. Okay, so it consists of thin opaque disc. Now what is means of opaque disc? Generally opaque disc is nothing but a circular disc which consists the appropriate holes on its periphery. Okay, so generally on disc periphery there are appropriate holes are present, and these particular holes are equal to the total number of rotor teeth. So generally the number of holes which are present on this opaque disc, that holes are equal to the number of teeth on its rotor periphery. Okay, so now there is a transmitter and receiver, so or emitter and receiver, because we have to sense the position of this particular rotor. So this opaque disc is generally fixed on the rotor, and on one side of opaque disc there is a photoemitter. Photoemitter is actually a transmitter that emits the light signal, and on another side there is a receiver. or in simple you can say that are the encoder and decoder. Okay, so there is a one photo emitter and one photo detector. So these photo emitter and photo detectors are placed along the periphery on either side of disk. So if we place, say, in general, if we draw the simple diagram of this particular stepper motor, then there is a stepper motor. On shaft of this stepper motor there is a opaque disc which consists the equal number of holes on its rotor periphery, and that number is equal to the number of teeth which are present on this rotor shaft. Okay, so there are holes present on this opaque disc. Now on one side we use a photo emitter. That photo emitter emits the light signal. On opposite side of this particular opaque disc there is a photo collector, okay, or photo detector. So these photo emitter and photo detectors are placed along the periphery on either side of this disc. So whatever light which is emitted by the photo emitter is received by the detector placed on its opposite side when a hole on disk came in between them. So whenever there is a hole came in between this light source, then whatever light which is initiated by this photo emitter, that light source is fall on the photo detector. Okay. Now number of sensors is equal to the number of switching devices for the exciting the phases of winding. So how many sensors are there? That sensors is equal to position sensors. How many position sensors are there? The number of position sensors are equal to the number of phases which are there on a stator of this stepper motor. So now for this particular case, the stator is here 4-phase stator. Therefore, we use a 4 position sensors. So each position sensor generally sense the particular position of a rotor. So the number of sensors equal to the number of switching devices for exciting the phase winding independently. Okay. So now how these position sensors are placed. So basically these position sensors are placed at a distance of 360 degree divided by NR plus step angle. Okay, so this is the formula for placement of position sensor. So there are number of position sensors and that number is equal to number of stator phases, and this number of position sensors are placed at this particular distance from each other. Okay, so they should place at a distance of 360 degree divided by NR plus step angle. So where NR is what? It is the number of rotor teeth. Step angle is theta s. Okay, so that step angle you are familiar with how to calculate that step angle for variable reluctance stepper motor. So that is 360 degree divided by N into NR. So that is actual step angle. So we have to add that step angle in 360 by NR to determine the actual position of these sensors, that is the position sensors. So depending upon the direction of rotation and the required step angle, the phases are switched on. Now, a logic translator is used to accomplish this function. So this phase initiation pulses, that is the whatever logic sequence which is required for initiation of these phases or for excitation of these stator phases, that logic sequence is generated by a logic translator. Okay. So the signals for the translators are obtained from the comparator. So there are two signals required for this translator. One signal is obtained from the comparator that depends upon the required number of step angle, and another signal is generally taken from the actual position of rotor, that is from position sensor. Okay. Now these two signals are taken. So the comparator compares the number of steps of motor is required to move through with the actual number of steps which are completed. So basically one input is required number of steps and second input is actual number of steps to be completed. So comparator generally compares that two numbers. So how many number of steps are actually required for the motor and how much steps have been completed by that particular motor, and accordingly the digital comparator will initiates the one control signal or one input signal to this translator. The another input signal to this translator is actually the output signal of this position sensors. Okay. Now the translator feeds the gate driver circuit of this power converter switching devices through amplifiers. So whatever logic sequence which is generated at the translator output, that logic sequence is amplified using amplifier, and this logic sequence or these pulses are given to the gate driver circuit of the power converter switches. Okay, this power converter is nothing but uh, the excitation circuitry which is provided to each stator phase that consists certain power switches, and these power switches gate circuit is excited through this logic sequence which is generated by the translator, and according to this particular logic sequence the particular phase excitation circuit will switch on, and then the motor will runs with the a desired step angle for a next step. After completion of that next step only the next initiating pulse is given to the excitation circuitry. So in this way the closed loop control scheme of a stator motor will operates. It requires the inputs for logic controller from two different uh, sides. One input is actually the required number of steps, and second input is actual position of the rotor. So according to the required number of steps and the total number of steps that have been completed by the rotor, the one initiating pulse or one input to translator is provided. So there is a simple comparison between the number of steps required and number of steps completed, and accordingly digital comparator provides a first input to translator. Second input to this translator is actually the position sensor. Okay, that is the output of this position sensor, that is the second input, and accordingly this translator will generate the logic sequence. Okay, so this is how the closed loop control strategy of the stepper motor will work. Okay, so here we have discussed these two control strategies. One is the open loop control strategies and second one is closed loop control strategy. So question might be asked for 5 marks on individual control strategy. Write a short note on open loop control strategy, or maybe write a short note on closed loop control strategy. So if such question is there, you have to draw simply block diagram and you have to write explanation. For 10 mark question may be asked, explain open loop and closed loop control strategy. Okay, so according to the question which is asked in examination, you have to write your answer.